Now, we're going to discuss another topic inside Carbanion that is known as hyperconjugation. Now, what is hyperconjugation? Hyperconjugation is something which is known as a no bond resonance. So, there is resonance, but without the pi bonding, or the sigma bonds kind of show a type of resonance. But here our concern is that we have to remember that hyperconjugation only exists in carbocation and not in carbanion. So we have to keep a point in mind that there will be no hyperconjugation in carbanion. Why? Because if I draw a carbanion, say I have C and H again, and I have a CH3, but with a, okay, so this CH3, the CH3 here is now losing a, an H positive and converting into a, now we'll convert this into a carbanion. So how do we do that? We just CH2, it becomes CH2 with a negative sign. So this is a carbanion for us. And what I want to show you that there is no hyperconjugation because this CH, this CH bond will take one CH, all of them are similar. So this CH bond has electrons. We know that bond is made up of, the sigma bond is made up of electrons. Now these electrons and this negative charge, they repel each other. They repel each other. And when they repel each other, no hyperconjugation occurs because they are so unstabilized. So these electron density, both of them, they have electron density, and electron density in each one of them, what it does is in each one of them repels, and the electron density, the both possess electron density and that repels, and thus thus no hyperconjugation occurs. So no hyperconjugation occurs in a carbanion. So this possibility we have to remove that of any hyperconjugation occurring in the carbanion. Now moving on, there is another topic that we're going to discuss and just providing a little idea onto it is that the concept of most acidic hydrogen. Now, when we were forming the carbanion in the first place, we said that when CH4 was losing an H positive, we said it was forming a CH3 negative. Now, this CH3 negative was when it was being formed, we were releasing an H positive, and this H positive here is the most acidic hydrogen. So we can just say that the most acidic hydrogen is that one which is released, or why it is known as the most acidic hydrogen is because it comes from an acid. So it is provided by an acid and therefore it is referred to as an acidic hydrogen. So when we remove this H plus, the corresponding carbanion which is formed, and if this carbanion is stable, then that hydrogen is going to be the most acidic hydrogen. Now this is when we're comparing them. Now next, before I present you with an example, please note that when I remove, on removing, when I remove the H positive, okay, the corresponding, whatever corresponding C negative, that is the carb anion is formed, we are getting the corresponding carbon ion, which is the most stable. So if this carbon ion is the most stable one, then that acidic hydrogen is known as the, then H plus becomes the most acidic hydrogen. So what we are saying here is when I remove the H positive and I get a carbon ion, whatever is the most stable carbon ion, that H positive becomes the most acidic hydrogen. So what happens here is we have example here. This is an example that I'm providing you with, and let us see. So we have got first, the second one, and the third one. Now in this example, if I remove H positive from each one of them, say I remove H positive from with this one, again, please note that the H here and the H here is the same. So any H I remove doesn't affect the answer that I get. So all of them have similar H. So let us start by removing an H positive, and I obtain CH caused with a triple bond, and then I have C with a negative sign. Okay. Again, I remove an H positive from this yet again, and I've got a CH2 with a double bond and a CH with a negative sign. So we are removing an H positive again from this one, and now I'm getting a CH3 along with a CH2 with a negative sign. And I have to compare the stability. So I have to tell you the order of stability in these. Now, what I'm going to do next is, because I have to compare the stability in each one of them, I am just going to write their hybridization. We'll see what that leads us to, but I start by writing the hybridization. So this one has an sp hybridization, okay, and because there are, you can see that there is 2 pi bonds in a triple bond. There are 2 pi and 1 sigma. You should know this. So there is 1 sigma bond and 1 negative charge acting as a lone pair. So we have an sp hybridized carbon ion here. Here I have an sp2 hybridized carbon ion, similar to that case, the previous case. We have got a sigma bond here, a sigma bond with H, and we have got a negative charge acting as a lone pair. So we have got an sp2 hybridization again here, and we have an sp3 hybridization here. So why I wanted the hybridization was, what we are going to do is, and we've been doing it for quite a while now, is that I'm going to see the electronegativity of them. So what I'm going to do is start writing all of them: sp, sp2, and I've got an sp3. Now the percentage s character in each one of them, if I am to write that, so the percentage s character comes out to be something like, in SP we have a 50% S character, in SP2 I have a 33.3% S character, and in SP3 I've got a 25% S character. So we have done this multiple times and we're going to do it yet again, is that if S character increases, electron negativity also increases. So here, if I am to write the order of electronegativity, so the order of electron negativity will be, order of electron negativity will be Sp greater than Sp2 greater than Sp3. So order of electronegativity, it is this way. Now we have done this, and we should be aware of this, that what I'm gonna do is, I'm gonna tell you, and that is, we have done it a couple of times now, that electron negative group, what it does is, it acts as an electron withdrawing group. So it is actually equivalent to an electron withdrawing group. So it is electron withdrawing. So the greater the electron negativity, the more is the electron withdrawing by it. So notice here that this is Sp, this is Sp2, this is Sp3. So what we have done here is, Sp is the most electron negative. So most electron negative, being the most electron negative, there will be more electron withdrawing from this carbon ion. So what happens is, if I am withdrawing the negative charge, I am getting a more stable carbon ion because I am neutralizing the charge. So the electron withdrawing nature is working to our advantage. So the negative charge makes it, the negative charge becomes more stable on that carbon ion which is more electronegative. So let me just write this statement here so that you don't forget it. So the negative charge is more stable on that carbon ion which is more electron negative. More electron negative. Now, which one is the most electron negative? Of course, the first one. The first one is the most electron negative, followed closely by the second and the third one. So, the order of stability will be this one greater than this one. So, if I am writing the order of stability, finally, what I'm going to get in the answer is that the order of stability will be something like 1 greater than the second one greater than the third one. So that is the final answer that I have been wanting. So if I am to tell you the final answer, it is that first is greater than the second is greater than the third. And this is how we decide on the stability of a carbanion, looking at the electron negativity when we have to. Okay.